Hello, everyone. I'm excited to walk you through an in-depth demonstration of the McGinty AI NDDC Universal Media Compressor. It's a revolutionary tool that leverages quantum computing technology and n-dimensional data processing to achieve compression ratios previously thought impossible. This cutting-edge compression system uses the proprietary McGinty equation, or MEQ, and it projects data into higher dimensions, identifying fractal symmetries, and it applies quantum superposition for dramatic file size reduction. Let's explore all the features and capabilities of this futuristic system. First, let's look at the interface. At the top, we have the McGinty AI branding with the Cognospheric Technologies Division logo. Notice the system indicators showing ZPE extraction at 98%, quantum coherence measured in microseconds, and the optimal fractal integrity. The title shows that we're working with the NDDC Universal Media Compressor, which stands for N-Dimensional Data Compression. The small badge indicates it's capable of dimensional processing from D3.5 all the way up to D13.3, which, as we'll see, enables some extraordinary compression capabilities. The interface is organized into three primary tabs: the compression engine, the 4K Media Lab, and the NDDC Function Tuning. The compression engine is our main workspace for processing files. The 4K Media Lab is specialized for high-resolution video compression. And then the NDDC Function Tuning is for advanced users who need really granular tuning. Notice that the 4K Media Lab has a Pro badge and that the Function Tuning has a Pro Plus badge, indicating that they're premium in nature. Let's start with the main compression engine to understand the basics. The main view is divided into input and output sections. On the left, we'll select and configure our input file, and then on the right, we'll show our compressed results. Below the tabs, you'll see the McGinty AI tagline indicating that it's the official n-dimensional data compression implementation, and then the small blue badge confirms that we're using the patented MEQ technology, which is the mathematical framework that makes this all possible. Now let's upload a file to compress. I'll click on this upload area and select a file. Perfect. I've selected a technical white paper PDF of substantial size, 144 megabytes. The system has automatically recognized it as a PDF file, and it shows us the current file size. Now, before we compress it, let's take a look at the compression settings. I'll click on the Show Settings panel to explore our configuration options. The most important setting is the fractional dimension slider. This determines how many dimensions the data will be projected into during compression. The current setting is D6.6, which the system tells us will provide approximately 12:1 compression. Let's increase this to see how it affects our potential compression. I'll move it up to D9.5. Now we're looking at a theoretical compression ratio of about 90:1. That's quite remarkable. Notice how the visualization below the slider shows us the range from 3.5, which gives us minimal 2:1 compression, all the way to 13.3, which offers an extraordinary 10,000:1 ratio. Next, let's look at the quantum resources. This slider controls how many qubits are allocated to the compression process. More qubits generally mean higher precision and lower error bounds, but it may require more processing time. I'll increase this to 350 qubits. The PNX function tuning allows us to adjust the mathematical parameters of the McGinty equation. This is the core algorithm that enables the n-dimensional projection. The default of 1 works well for most files, but different values can optimize compression for specific types of data. Under file type, we can specify what kind of file we're working with. The system has already detected our PDF, but we could change this if needed. Finally, let's set the simulation level to MEQ Enhanced to utilize the full capabilities of the McGinty equation implementation. Before we start the compression, let's take a moment to understand the NDDC dimensional visualization. This graphical representation shows how data is projected and manipulated in higher. The concentric circles represent the dimensional expansion. As we move the dimension slider, you can see how these projections change. The marker on the scale at the bottom shows our current position in the dimensional spectrum. Below the visualization, we can see our key metrics: the compression ratio based on our current settings, the quantum resources that are allocated, in this case 350 qubits, the quantum coherence time, which increases with dimensional complexity, and the MEQ scale, which represents the relative McGinty equation complexity. So now let's run this compression and see the technology in action. I'll click the compress button. The system is now processing our file through several phases. First, it's initializing the NDDC compression pipeline. Now it's calculating the fractal dimensions, identifying self-similar patterns in our data. Next, it projected the data onto a 9.5 dimensional space using the McGinty equation. It's applying quantum superposition mapping, which is where the quantum resources come into play. It encoded the fractal symmetries that it identified earlier. Since we selected MEQ Enhanced mode, it's now applying McGinty equation gravity corrections for higher dimensions. Finally, it's finalizing the lossless compression. And there we have it. The compression is complete. Let's examine the results. On the right side of the screen, we can now see our compressed file with its new size and detailed statistics. Here's the compressed file. Our original PDF was 144 megabytes, and it's been compressed down to just 1.18 megabytes. That's a compression ratio of 122 to 1. Which aligns with our theoretical prediction for D9.5. The compression statistics panel also shows us the original and compressed file sizes, the exact compression ratio achieved, the fractal dimension used, the quantum resources allocated, in this case the 350 qubits, the reconstruction error bound, which is extremely low, at 10 to the negative 7 power. The processing time was just under 13 seconds, and our PN factor and MEQ mode. Below the statistics, we can see a snippet of the McGinty equation implementation code that powered this compression. Notice the projection function that uses the exponential logarithmic relationships to maintain the data's integrity across dimensional transformations. Now let's verify that we can retrieve our original file by performing a decompression. I'll click the decompress file. The system's now reversing the process. First, it's retrieving the 9.5D space projection. Then it reconstructs the fractal patterns. Then it's collapsing the quantum superpositions back into the classical states. Then it applies the inverse dimensional transform, which then rebuilds the original data structure. And then finally, it's verifying the data integrity to ensure that nothing was lost. And it's complete. We've successfully retrieved our original file with no data loss. This demonstrates the truly lossless nature of NDDC compression despite the dramatic size reduction. Now let's switch to the 4K Media Lab to see how the system handles high-resolution video, which is one of the most challenging compression tasks. Here we have 3 sample 4K videos we can work with, each with different characteristics that will affect the compression. A beach sunset scene with smooth gradients and gentle motion, a city time-lapse with complex details and rapid changes, and then a wildlife documentary with natural textures and moderate motion. Let's select the wildlife documentary, which at 1.7 gigabytes represents a significant compression challenge. The system has loaded our video and showed the preview frame. Now we'll compress it using the NDDC technology by clicking the Compress with NDDC button. The compression process for the video is similar to what we saw for the PDF, but with additional considerations for temporal coherence, which is how the frames relate to each other over time. The compression is now complete, and we'll examine the results. The original 1.7 gigabyte file has been compressed down to 14.25 megabytes. That's a compression ratio of about 122 to 1 while maintaining full 4K resolution. The video quality metrics show that the resolution maintained 3,840 by 2,160, which is 4K UHD. The video frame rate was preserved at 60 frames per second. Quality loss rated as imperceptible. And then the peak signal to noise ratio was 52.8, which is exceptionally high. This level of compression while maintaining such high quality would be revolutionary for video streaming, storage, and distribution. For our final exploration, let's dive into the NDDC Function Tuning tab, which provides advanced controls for expert users. This section gives us a granular control over the fractal and quantum parameters that power the compression algorithm. Under fractal parameters, we can adjust fractal recursion depth, which determines how many levels of self-similarity the algorithm searches for, self-similarity factor, which defines the threshold for identifying patterns, and then the complex conjugate selection, which affects how the mathematical transformations are applied. Under quantum parameters, we can configure the quantum circuit topology, which defines how qubits are interconnected, and the entanglement model, which determines how the quantum states are correlated, and then our error correction approach, which balances accuracy against processing speed. Below these settings, we have custom PN function setting where we fine-tune the McGinty equation itself. The function shown here extends the basic equation with trigonometric components for even more sophisticated dimensional mapping. At the bottom, we can see the completed configuration in JSON format, which is perfect for saving presets or integrating with automated workflows. This JSON includes all of our current settings from the dimensional value to the quantum resource allocation to the custom function parameters. Let's go back to the compression engine and try a different file type to demonstrate the system's versatility. We're going to click the Change File button, and this time I'm going to select an image file. Okay, there you can see it there. So the system has detected this as an image file and generated a preview. Now I'll adjust our settings for optimal image compression. For images, a dimensional setting around D7.8 often works well, which balances size reduction and visual quality. Now let's compress the image. The compression process completes, and then we can see our original image of 2.7 megabytes is now been compressed down to 75 kilobytes. For an image, this is remarkable compression while maintaining visual quality. You may have noticed references to MEQ throughout the interface. MEQ stands for the McGinty equation, which is the proprietary mathematical framework that enables this revolutionary compression. At the very bottom of the screen, we can see some of the key components of the MEQ technology. Quantum superposition for leveraging quantum mechanical properties, fractal symmetries for identifying repeating patterns across scales, holographic encoding for representing data with dimensional redundancy, and the MEQ integration, which brings all of these components together in a unified system. The footer also mentions that this technology is protected by 28 international patents, highlighting its innovative nature. Before we conclude, I should point out a few additional features. There's a Share Results button, which will allow you to export and share your compression achievements with colleagues or clients. There's an Export Data option, lets you save your compression statistics for further analysis or reporting. And if we look at the system status again, you'll notice that all the indicators show optimal performance, with quantum coherence maintaining stability throughout our demonstration. This concludes our comprehensive exploration of the McGinty AI NDDC multi-universal media compressor. This quantum compression technology shows what might be possible in the future when quantum computing, advanced mathematics, and innovative algorithms converge. The ability to achieve even 100-to-1 compression ratios while maintaining perfect data fidelity would revolutionize data storage, transmission, and processing across countless industries. Imagine downloading 4K movies in seconds, storing months of surveillance footage on a single drive, or transmitting complex scientific models across limited bandwidth connections. While this particular implementation is futuristic, it represents the kind of technological leap that companies around the world will be taking. Thank you for joining me on this demonstration of the McGinty AI NDDC Universal Media Compressor. I hope you enjoyed this glimpse into what the future of compression technology might look like.